So far in thermodynamics, we've been considering macro states of the system, like pressure and temperature and volume. These are all things that have to do with an enormous collection of particles. As physicists, though, we have the power to get a little bit narrower. We could look at actually what causes pressure, and that's our goal today. We're going to be doing the kinetic theory of gases. And the idea is, kinetic theory of gases, it's really a beautiful derivation. It will take quite some time, and there are some assumptions that we have to start with. But let's start by making those assumptions. First assumption is that we have a large number. We have a large number of particles, and that they are all identical. Large N identical mass particles, and let's see, identical mass, and also point particles. That means that they have no volume. So again, this reminds you of the ideal gas law, because we because if they're point particles, they don't take up any space, and I could compress them infinitely, and that wouldn't be an issue. So I'm going to have to use these assumptions in key places today, but let's just throw that out there. Do you have any questions about that assumption?
No, I've actually got to go to English.
Okay, very good. Go to English. The second assumption is that we have a random distribution of collisions. Our collisions are not going to be predictable, and they will obey Newton's laws. Random collisions obeying Newton. And our third assumption is that those collisions are elastic. Elastic collisions, if you'll recall, please, means that there will be no energy lost when these tiny point particles run into each other. So if they have identical mass, one comes in, then the first one will stop and the second one will bounce out, just like ideal interactions. Macroscopic. It turns out that the assumption of elastic collisions is a very reasonable assumption when you're dealing with tiny things like these point particles. So I want to start by putting a particle in a box. It will be just a single particle. And here's our box of size L on every side. It'll be a cube. We got L that direction, L that direction, and L that direction. And my dot's going to be blue. And my dot is initially moving to the left. And my dot has some momentum because it's moving to the left, right? My dot is, well, let's set up some coordinate system here. We're going to say that this is y and that's x. And I'm going to say that the initial momentum of my speck of matter, let's say that it's got a mass m, the initial momentum of that sucker is going to be negative m times v in the x direction. I don't care how fast it's going. But the thing is, this speck is going to hit the left wall. And after it hits the left wall, it will be going the other direction in the x direction, right? In x, it will be going the other way. I actually don't care what's happening in the y direction or in the z, which would be towards us and away from us. I only care that when it hits this left wall, when it hits the left wall, it will change its direction in x. So I guess if it were to hit the top wall, it would change its direction in y. Okay, but let's just focus on the x for a moment. And this would be positive m times vx. So what if I asked you what the change in momentum is? You'd say, well, that's just final momentum minus initial momentum. And sure, it's actually 2 times mvx. 2 times the mass times the velocity in the x direction. All right, so if I asked you what force it must have felt, well, you could say that the force it felt was the change in momentum divided by the change in time, because that's Newton's second law. I'm going to continue with a different color so I don't get crowded here. I am crowded, so I'm going to continue with a different color. Let me say it like that. Then, this is 2 times m times v sub x divided by, well, it's going to be divided by the time. How long does it take that sucker to do that change in momentum? How long would it take between one hit and the next hit. I guess that would be, well, let's see, it's gotta go, oh shoot, it's gotta go this way, and then back that way, and then this way again. So on average, the amount of time it's gonna take, now this is a little bit tricky, maybe this is okay with you, the time that it takes, time between collisions, if I just let this sucker continue to hit that left wall, the time between collisions is going to be, well, I guess it'll be the distance divided by the velocity in the x direction. And the distance that it goes in the x direction, I'll put d sub x, and the velocity in the x direction. The distance it has to go in the x direction is 2L, and then the velocity in the x direction is what I'm just calling v sub x. So I can take this and plug it in down here. So I will divide by 2L over v sub x, put another equal sign here. Oh, I'm getting something lovely coming out here. Look, I've got my 2's canceling. I've got my vx's. Wait a second, are the vx's canceling? Are they or not? Look at this. If I'm gonna go back to green right now, nope, can't do green, too soon. So my 2's cancel, but I get m times vx square over L. Now, of course, I'm not just interested in force. I'm interested, that's the force on the wall, right? Or maybe it's the force on the particle. Either way, it's gonna be an average force smoothed out over time. This always works for the x component of one atom. And my next plan then is to figure out what the pressure on the wall is. So, let's go back with green again. Pressure on the wall is that force divided by area. So if I take that force, which is mvx square over L, and then I divide that by area, that's L square, that's the area of that wall right there. This wall, that wall on the left has area L square. Well, this is just mvx square over over volume. Okay, but see, Maxwell notices that there's a distribution of these velocities, and this was Maxwell's first huge contribution to physics. He says some particles in a gas, if I now allow there to be a large number of particles, some of them are going very fast and others of them are going very slow. And you would bet that the amount going fast and the amount going slow depends on the temperature. So I'll just draw you a couple different graphs of the probability. These are the first of our probability graphs. This is speed on this axis right here. And this is the probability of probability. Yeah, sure. This is the probability of finding one of the particles at a certain speed. Now you can bet that at a large temperature, there are going to be a lot of fast particles, but you probably won't find a lot of extraordinarily fast particles. But you don't have a lot of slow particles, and so it's going to be doing something like this. It'll be like, woo! And ultimately, you won't find any particles going the speed of light. That's crazy. That's probably way out here or further out there. But you'll find a lot of fast particles, and if you have, well, this would be a high temperature. Let's all say this is something like 1,000 Kelvin. No, let's say 1,100 Kelvin. That's really hot, right? But you could also have a much cooler situation. Oh yeah, cool. Where on average, the particles would be going much slower. But the interesting thing that I'd like to point out with this graph is that there are some particles in the gray. This is cool. This might be room temperature gas. At room temperature, the particles here, some of them are going faster than some of the particles in the hot gas. And that's okay. But I'm just saying it's more likely that any given or any typical or an average particle is going faster with a hot gas than it is for a cool gas. So I'll put a dotted line right here and say that this is the most likely speed. The most likely. We're going to get in all kinds of different kinds of averages, but this is the most likely at 1,100 Kelvin, and this is the most likely at 300 Kelvin. So the most likely speed to find, the most common, or the Well, I think that's fine to call it like that. The most common speed is here, and the most common speed is there. It's probably not the same as the mean, but we can work on that later. So this is Maxwell's contribution. Maxwell, his first contribution of many things. Maxwell did some awesome physics. Maxwell says there's a distribution. And now we can go back to that, whoa, how many eyes do you want there? Next, we can go back to this equation right here. We said that pressure on a wall, I'm gonna write it back down for you again. Pressure on the wall is mass of a particle times Vx square divided by the volume of the container. And what I want to do next is I want to say, what if there are multiple molecules? Then I can argue that the pressure for lots of particles, the pressure will be, well, it's going to be the mass of all of them, right? It's going to be the mass of all of them times V sub x square average. We want to take the average value of those suckers and divide by the volume. But my next point is to say, if we have lots of particles, we can't just say the mass of one of them. We need to multiply that by capital N, the number of the particles. And capital N will be a very large number. I'm just going to write this slightly differently. I'm going to pull out N over V and then say I need to multiply that by Vx square average. And I hope that's all right with you. My next step is to point out to you that there's nothing special about the x direction. The x direction is exactly the same as the y and is exactly the same as the z in and out on this diagram. And so we can notice that v square, here's this idea, the vector v velocity square is equal to the vector x velocity square plus the vector y velocity square plus the vector z velocity square in 3 dimensions, right? And I also want to tell you that the average speed in the x direction square is probably equal to the average speed in the y direction square. If these things are really the same, if these directions are all really symmetric and I'm in a cube of a certain volume, then I can say that these averages should be the same. There's nothing special about x, is really my point. And then I can say that this is also Vz square. If I take the average speed, I'm going to take the speed of each molecule and square it and then take the average. It's important to notice my parentheses here. I'm not taking the average speed and then squaring it because the average speed is 0 in the x direction. All right, so the point is, if each of these are equal, and if I want the average of this, then the average of this is just 3 times this average. And I guess it's 3 times that average, and it's 3 times that average, because these directions are all equivalent. So my next step, well, I guess I'm going to take this equation right here, and I'm going to write down, I guess I'm going to say that V square, I'm going to square the total speed and then take the average. That would be equal to 3 of Vx square average, because they're each the same and because the V square is the sum of all of those. So let me just say that that would be, well, on average. It is very important that I'm taking that average. On average, I've got 3 times Vx square. All right, okay. All right, so that's what I'm going to say as I continue to move on here. I'm going to argue that, there's another way we could look at this. We could also say that Vx square average is the same thing as 1/3 V square average. So this is speed. This is velocity in the x direction, but this is actual just figure out how fast the dang particle is going. All right? So I'm going to then say, oh boy, here's where it gets really good. We'll go purple for this. Pressure. Now, we had this equation for pressure. Let me remind you what it said. It said pressure is N over V times mVx square average. And I'm going to say now that pressure is 1/3 N over V times mVx square, mv square, average. But this right here, we can identify what this thing is. mv square. Well, that's related to the kinetic energy. Is it the kinetic energy average? No. How is it related to the kinetic energy? Well, it's twice it. All right, super. So now I can say, oh boy, this is getting even better. Watch this. Pressure is 2/3 N over V times the average kinetic energy of a particle. Fascinating. All right, let's continue here. Let's continue, or maybe I could write it in just a slightly different way. I mean, just to show the kinetic energy average, 2/3 N over V. I'm motivating this dividing by 2. Now I'm going to say 1/2 mv square, and I'm going to say that that's our average kinetic energy. Okay, and then I can, oh dang! Remember that pressure times volume has units of energy? I'm going to look back at this pressure times volume thing. We're getting very close to a final realization here. So this is pressure times volume, you'll recall, is N times K times T, where this is the number of particles, and this is the Boltzmann's constant. We can put a little b down there for you. And this is the temperature of the system. Now I'm relating microscopic quantities like the speed of the particle to macroscopic quantities like how much stuff do I have and what temperature is it, and what's the pressure and what's the volume. This is about to be awesome. Now I want to tell you that this stuff right here, that is 2/3. Check it out. I'm not going to have a V anymore because I'm supposed to multiply by V, so it'll cancel that right out. That's 2/3 times N times 1/2 mv square average. But look at these two N's right here. I'm going to take this equation right here. I'm going to look at it in just slightly more detail. KT, Boltzmann's constant, times the temperature of the sample is equal to 2/3 times the average kinetic energy of a particle. And what if I wasn't so interested in the temperature? What if I was interested in the average kinetic energy of the particle? Check this out, and I'm going to go back to our AP language also. I'm going to stop saying kinetic energy as KE. Let me do that explicitly. This is going to be K. Average kinetic energy. Of course it's a capital K because I don't want to confuse it with Boltzmann's constant. Here we go. I'm going to say since Boltzmann's constant times the temperature is 2/3 times the average kinetic energy, I can conclude that the average kinetic energy of a particle in a gas is 3/2 Boltzmann's constant times the temperature of that gas. And this is what we've been working for. You can now tell me if you know the temperature of a gas, the average kinetic energy of a gas within it. This is a new definition of temperature. Now we know what temperature actually means. And I'll close with an oh snap. Just kidding, I'm not even closing. Oh snap is what I want to say about that. And I also want to point out that this is for a particle in a 3-dimensional box. So I guess I could say that particle, each particle in there, has 3 degrees of freedom. Which means it can move as fast as it wants in the up and down, as fast as it wants in the over, and as fast as it wants in the forward back direction. So it has 3 degrees of freedom, and guess what? Every degree of freedom provides 1/2 K times T of kinetic energy. And then we'll just say, dang, and let you soak that sucker up. So if you had 5-dimensional space, the average kinetic energy of a gas would be correspondingly higher. Or, I guess that means if you had more dimensions of freedom, if you had more degrees, the way that something could move, then the temperature would be correspondingly lower. So degrees of freedom represent a method of storing energy. The more degrees of freedom, that's this number right here. The more degrees of freedom, the more efficiently your gas can store energy. This is beginning to justify heat capacity and specific heat. Bye. Are not going to be predictable, and they will obey Newton's laws. Random collisions obeying Newton. And our third assumption is that those collisions are elastic. Elastic collisions, if you'll recall, please, means that there will be no energy lost when these tiny point particles run into each other. So if they have identical mass, a beautiful derivation, it will take quite some time, and there are some assumptions that we have to start with. But let's start by making those assumptions. First assumption is that we have a large number. We have a large number of particles, and that they are all identical. Large N identical mass particles, and let's see, identical mass, and also point particles. That means that they have no volume. So again, this reminds you of the ideal gas law, because we because if they're point particles, they don't take up any space, and I could compress them infinitely, and that wouldn't be an issue. So I'm going to have to use these assumptions in key places today, but let's just throw that out there. Do you have any questions about that assumption?
I've actually got to go to English.
Okay, very good. Go to English. The second assumption is that we have a random distribution of collisions. Our collisions, so far in thermodynamics, we've been considering macro states of the system, like pressure and temperature and volume. These are all things that have to do with an enormous collection of particles. As physicists, though, we have the power to get a little bit narrower. We could look at actually what causes pressure, and that's our goal today. We're going to be doing the kinetic theory of gases. And the idea is, kinetic theory of gases, it's really gas one still, one comes in, then the first one will stop and the second one will bounce out, just like ideal interactions. Macroscopic, it turns out that the assumption of elastic collisions is a very reasonable assumption when you're dealing with tiny things like these point particles. So I want to start by putting a particle in a box. It will be just a single particle. And here's our box of size L. On every side, it'll be a cube